The name of this video is Electrostatic Potential Basics. Given an electrostatic field E, such a field is conservative if and only if the curl of E is equal to vector 0 in a simply connected domain. I remind you that we already discussed the simply connected domains in a previous video. This is a necessary and sufficient condition, NS, necessary and sufficient, if and only if. Under these conditions, E can be written as minus the gradient of a scalar field, capital B. This scalar is what we call the electrostatic potential. Note that here we are using the convention with a minus sign. Why do we use this minus sign? In order to understand this, think of a mountain. This is the profile of such a mountain, which can have many ridges that allow us to reach the summit if you want. What the gradient on its own does, if we represent this mountain by means of a curve in 3 dimensions, the gradient is like a compass, and this compass tells us the maximum steepness on this surface. And so in this case, for example, it could be that the maximum steepness is along this ridge line, that eventually brings us to the summit. So this is the maximum steepness. Now, if you make a comparison with an analogy with gravitation, typically we want to express conservative fields in such a way that if I wear a mass particle, so a particle with a mass, I want to fall into the field lines, which in this case are these ridges on this mountain. And so I want to invert this mountain. And how do I invert this mountain in math? Is by adding a minus sign. And so I end up with a valley, if you want. So we begin with a mountain, and we end up with a valley. Okay? In this case, minus the gradient tells us what is the descent path of maximum steepness, which allow us to go to the bottom of the valley if we were a mass particle. We would fall in this direction. This is the analogy with gravitation. That is why also in electromagnetism we choose a minus sign. Okay, so now we know that the electrostatic field E, which is a vector field, and note that what we are trying to do with the electrostatic potential is to move from vectors, which are complicated to deal with because they are made of many components, to a scalar function, which will allow us to solve the problem in a much simpler fashion, using again scalars. So we know that vector E is a central field with a spherical symmetry. And we know that we can write this field by means of Coulomb's law, 1 over 4 pi epsilon naught q divided by r squared in the UR direction, if we were to use, in this case, a spherical coordinate system, which obviously makes sense, because this is the symmetry of this field according to Coulomb's law. Now, suppose that this field is generated by one single point-like charge particle in space with charge small q, and this is located at the, as always, our source point capital Q. And suppose that we want to use a test particle Q naught and move it from a point R naught away from capital Q. This is point capital P naught. Here I place my charge Q naught, as always, our test charge, and the test charge, we want to move it to another point. Let's call it a generic point capital P. There again we have Q naught. I remind you that we already know that because of the rotational property of the electrostatic field, it doesn't matter the path we follow to go from P naught to P. We can follow any path we want. And so if we do that, so now we want to find the electrostatic potential by means of this definition associated with this tangential field. So how do we proceed? The way to proceed in this case is to use this very definition with respect to the spherical coordinate system we have chosen to work with. In a spherical coordinate system, for a vector field which has only the radial component, then this gradient becomes nothing but, in general, the partial derivative with respect to r, but since we only have one component and one variable r, it becomes the total derivative, if you want. Therefore, we can write E, let's invert it. So we start with the gradient of V, and the minus sign, we bring it to the other side. So the gradient, again, in a spherical coordinate system becomes the partial with respect to r, but again, we can write it as it turns out, as the total derivative. Let's leave a little bit more space. We can write it as the total derivative d of v, which will be also a function only of r, okay? So I took the numerator of the gradient in a spherical coordinate system, which is d of vr, okay? Remember that this has to be derived with respect to dr. So this has to be equal to minus, we bring it to the other side, so it's minus 1 over 4 pi epsilon naught. So again, I'm trying to solve this differential equation with some boundary conditions, which I will set in a minute. That is, I need to integrate it. So 1 minus 1 over 4 pi epsilon naught, and again, because this minus, I bring it to the left-hand side here. This is dv, okay, and here we have q, which is also constant. Okay, so then we have 1 over r squared, well, ur, which is also constant. And finally, the variable which eventually we need to integrate. So I leave some space here for the integration. And here we're going to have 1 over r squared, which is this function here. We need to integrate with respect to which variable? R. Remember that this gradient in a spherical coordinate system becomes nothing but d of r over dr. So we need to integrate over dr. Okay. So now let us to integrate. So how do we integrate between these two boundary conditions? So we need to integrate here between these 2 points, P naught and P, that is between R naught, and let us call this vector distance here simply r. Similarly here, we need to integrate, or we are integrating the total differential of v, and so we need to integrate between v at what point? At r naught, and v at what point? R. Okay, so this is the integral we need to use, we need to solve in this case. This is a pretty simple integral. It will give us as a result, since this is the total differential, Vr minus Vr naught equal minus all these constants. The integral of 1 over r squared, we know that is nothing but minus 1 over r. With the minus sign cancels. So let us remind ourselves here that this integral will give us minus 1 over r, okay? But with the minus sign, these two minus signs will cancel out. So let's continue our calculation. So here we obtain the total differential, which is v at r minus v at r naught. This has to be equal to all these constants and obviously here we forgot that the gradient needs to have also a vector component. So we need to remind ourselves that here there is ur equal minus of this quantity. Here obviously we have ur. So this ur in fact cancel out with this ur, so we don't care anymore when we solve this integral. We are only along one direction. So we got rid of that, so we get this. This minus sign cancels with this minus sign, so we obtain 1 over 4 pi epsilon naught q. What about here? Well, the minus sign cancels, so we have 1 over r integrated between r naught and r. So it's going to be, at the final point, 1 over r minus the initial point, which is 1 over r naught. All right, so now we know that this quantity here, as well as this quantity here, are constants. So we can group them all together and obtain down here the function which we wanted to find, v of r, equal 1 over 4 pi epsilon naught 1 over r. And then let's group together these two variables. So I bring this quantity to the right hand side, so I change the sign. And so we obtain plus, let's open a bracket, v of r naught, which is not positive on the right hand side, minus 1 over 4 pi epsilon naught q times 1 over r naught, which is also constant. This quantity here we call it the constant of integration, capital C. All right, now let us suppose that we want to set this C. This C, it's an arbitrary constant. So C is arbitrary. So now we want to set C at this point, capital PR. And this point, capital PR, is at a distance capital R from the source charge Q at capital Q. So we want to set the arbitrary constant C at this point such that the electrostatic potential V at that point, capital PR, is equal to 0. Well, this means that 1 over 4 pi epsilon naught Q times 1 over capital R plus C at P capital R has to be equal to 0. This implies that C at point capital PR has to be equal to minus 1 over 4 pi epsilon naught Q 1 over capital R. So if we choose this particular value of the constant C at that point, it happens that the electrostatic potential is 0, right there. So in Piazza, I would like that you think, what happens if I want to set the electrostatic potential to be 0 at this point P naught, which is at the value R0, okay? So I want this one to be 0. So what kind of arbitrary constant do we need in this case? And I want that you think about this in Piazza. Lastly, there is a very special and very important case that we will use almost all the time in this course, which is called zero potential conditions at infinity. As it turns out, the limit for small r that goes to plus infinite of v of r is equal to 0 if and only if the arbitrary constant c is identically equal to 0. When c is equal to 0, you can see from here, this quantity is 0, 1 over infinite gives me 0. This function is called a green function. In this case, v is defined as a green function for normal conditions at infinity. Unless otherwise specified, all electrostatic potential functions encountered in this course will be of this type. So we will set C to be equal to 0. This is particularly true for a single point-like charge in space, and it can be true also for any limited charge distribution. All right, so to summarize this video, we introduced the basic concepts of electrostatic potential. So in this first panel, we wrote down the necessary and sufficient conditions for E to be conservative, which means the curl has to be equal to 0 in a simply connected domain. This implies we can write E as minus the gradient of V, where V is a scalar function, and potential. We want to move from a vector to a potential, much easier to deal with. We then consider the case of a single point-like charge in space. This generates Coulomb's law, only in the radial direction. Therefore, the gradient can be written in this simple fashion in the radial direction. Let's remember there is a minus sign. We can rewrite this as a differential equation by moving the dr next to E, which is what we do here, dr next to E. Let's remember these directions. Then we integrate between the boundary conditions. For example, we want to move from point P naught to point P, and that's what we get. We end up having a constant of integration defined as such, which is arbitrary. For example, if we want the potential, and this is what we've seen in the second board here, the second panel, if we want the potential to be 0 at the generic point capital PR, we need to set C at that point equal to this value. More in general, typically we want to define, and this is what we discussed in this third panel here, we want to use green functions for normal conditions at infinity, which means we want to set C equal to 0, which is true for a single point-like charge or for any limited charge distribution. In this case, the limit for r equals to plus infinite of the electrostatic potential is equal to 0. That's it.